Now, we're going to discuss the Kolmogorov-Smirnov two-sample test. As discussed earlier, in the KS1 sample test, nag-evaluate tayo ng agreement between the CDF of a single sample and the specified theoretical distribution. Pero sa KS2 sample test, nakafocus tayo sa empirical cumulative distributions ng dalawang independent samples para ipagkumpara yung values nila directly and malaman kung nanggaling ba sila sa same population or hindi. Note na yung KS2 sample test is sensitive between distributions, which makes it an effective tool for identifying any type of difference between the distributions of the two samples. The rationale behind this is kung yung two samples are from the same population distribution, then ina-expect natin ang cumulative distribution ng both samples na yon ay close to each other. And if meron mang differences, it should be due to sampling variability or random fluctuations lang. Pero kapag meron ng significant difference at any point, then pwedeng nanggaling nga sila sa different populations. In other words, a large difference between cumulative distributions of the two samples suggests evidence for rejecting HO, which means na most likely, yung samples natin ay hindi nanggaling sa same population. In this test, we have two independent random samples of sizes m and n, that is from x1 to xm and y1 to yn, while their corresponding order statistics from continuous populations fx and fy are x1 to xm and y1 to yn. Note that these are sorted in ascending order. In KS2 sample test, we have three assumptions. First, the x's are mutually independent and identically distributed, given that the observations x1 to xm are random samples from a certain continuous population. This goes the same with the y's. Second, the x1 to xm and y1 to yn are mutually independent. That is, we assume independence between two samples. Lastly, the data are measured on at least an ordinal scale. Now, let's move on to the procedure. Meron tayong different hypotheses for different cases. For the two-sided case, we are testing against the null hypothesis that f1 of x is equal to f2 of x for all x. In other words, walang difference sa distributions ng dalawang samples. While the alternative hypothesis implies na merong at least one point na magkaiba yung distributions nila. Ngayon, pagdating sa one-sided cases, yung null hypothesis is nagsispecify ng directional relationship between the two distribution functions. For the upper one-sided case, sinasabi ng alternative hypothesis na yung distribution function f1 of x is strictly greater than the distribution function f2 of x. While sa lower one-sided case naman, sinasabi ng alternative hypothesis na yung distribution function f1 of x is strictly less than the distribution function f2 of x.
For step number 2, we will compute the test statistic. The combined sample of m plus n is first arranged in ascending order of magnitude. We let S sub 1 of x and S sub 2 of x respectively designate the sample or empirical distribution functions of the observed x's and observed y's. So for the formula ng S sub 1 of x, this is equal to the number of observed x's that is less than or equal to small x all over the value of our n. And for the S sub 2 of x, this is equal to the number of observed y's, which is less than or equal to our small x, all over the value of our n. The test statistic for our three sets of hypotheses are as follows. For the two-sided case, d is equal to the maximum value that we computed from the absolute value of the differences between S sub 1 of x and S sub 2 of x. For the one-sided case wherein our alternative hypothesis is that f sub 1 of x is greater than f sub 2 of x, d plus is equal to the maximum value that we computed from the difference between s sub 1 of x and s sub 2 of x. For the last one-sided case wherein our alternative hypothesis is that f sub 2 of x is greater than f sub 1 of x, d minus is equal to the maximum value that we computed from the differences between s sub 2 of x minus f sub 1 of x. Now for the decision criterion, we will reject HO at the alpha level of significance if the appropriate test statistic, which is D, D plus, or D minus, exceeds the 1 minus alpha quantile given in first, table 8.18a if our sizes is equal or m is equal to n. And the second one is table 8.18b if m is not equal to n or we have unequal sizes. Now let's move to large sample approximation for equal sizes. For n greater than 40, critical values can be obtained by using the following expression given in the table, corresponding to the 1 minus alpha quantiles and the type of alternative hypothesis. The table for this would be table 8.18a. So for example, we have n which is equal to 45, and we know that this is greater than 40. We have alpha which is equal to 0.05, and we are testing against an alternative hypothesis that is one-sided. Hence, we will be looking at the row of one-sided tests, and we will be locating 0.95, since 1 minus alpha, which is 0.05, is equal to 0.95. Looking at the corresponding expression below, we have 1.22 all over square root of n. So by just plugging n, which is equal to 45, we can now get our critical value. For the case of unequal sizes, when either m is greater than 16 or n is greater than 20, critical value can be obtained by entering the observed values of m and n in the expression given in the table corresponding to the 1 minus alpha quantiles and the type of alternative hypothesis. The table for this would be table 8.18b. So same with the procedure in the previous case, just look at the appropriate expression and compute for the critical value. Note that we will be rejecting HO if our computed test statistic exceeds the computed critical value. Okay, so ties within and across samples can be handled by considering only the R distinct ordered observations in the combined sample as values of x in computing S sub 1 of x and S sub 2 of x for R less than or equal to m and R less than or equal to n. And then we find the empirical CDF for each different x and their differences at these observations, and then we will calculate the statistic in the usual way. So in cases na may ties tayo sa mga values ng category X and Y, we can just proceed in usual way of arranging these values in ascending order, and then continue computing for necessary values just like what is stated in the procedure. For example, may na-observe tayong dalawang 4.5 sa category X out of M observations, and 1 sa category Y out of N observations. In arranging these values, isang 4.5 lang ang ililist natin sa table. The only thing that will change is the value of S sub 1 of x since magiging 2 over n na siya. For the remarks, we have two. First, if the two population distributions represented by the two samples are continuous, the test as outlined is exact. If the distributions are discrete, the test is conservative. So the point of this first remark is that if we use KS test for continuous distributions, it will be an exact test. And when we say exact, it means na yung makukuha nating p-value sa test na ito is accurate. And when we have an accurate p-value, mas magiging accurate din yung magiging decision natin for our null hypothesis. Unlike when we use KS test for discrete distributions, mas nagiging conservative yung test. And when we say conservative naman, it means na yung makukuha nating p-value ay madalas na larger values than they should be. And alam natin na if our p-value is large, we tend to commit type 2 error or the error of accepting HO when it is false. On a positive note naman, minimake sure naman ng KS test na hindi ito palaging magko-commit ng type 1 error or yung error of rejecting HO given that it is true. So in general, mas nagiging cautious lang talaga si KS test in finding differences among the compared distributions kaya tinawag na conservative. For the second remark, which is about power efficiency, when compared with the t-test, the Kolmogorov-Smirnov test has a high power efficiency of approximately 95% for small samples. As the sample size increases, the power efficiency decreases slightly. Compared to the chi-square test or the median test, the Kolmogorov-Smirnov is also more powerful in all cases. And lastly, compared to the Wilcoxon-Mann-Whitney test, The evidence seems to indicate that whereas for very small samples, the Kolmogorov-Smirnov test is slightly more efficient. However, when samples are large, the converse holds. So ang point naman ng remark na ito ay nagpo-focus sa dalawang bagay. First, ang KS test ay mas powerful or may high power efficiency compared with t-test, chi-square test, median test, and even Wilcoxon non-Whitney test. And when we say power efficiency, it is the ability of our test statistic to reject a null hypothesis given that it is false. So if mas mataas yung power efficiency, mas mataas din yung probability of making the right decision. However, ang second point ng remark na ito is that mas magiging high lang ang efficiency ng KS test for small samples. For large samples, the power efficiency slightly decreases.